Welcome to the class. I'm beginning to forget what it feels like to having students in the classroom. So finally, after more than 2 months, we are now able to host students in the real classroom. So welcome. A quick summary to what we covered last Wednesday. If we have external magnetic field applied in space, and if we have a magnetic material, this material can produce induced magnetic dipole moments, okay? So the magnetic dipole moment also generates its own magnetic field or flux lines, right? So in this case, what I'm trying to draw is I have applied magnetic field, which is out of the paper, into your eyes. For that reason, the current being induced in the dipole moments have to conform to the right-hand rule. So the current is flowing in the counterclockwise direction, right? Now, if you have a counterclockwise current, the magnetic field generated by this induced dipole is also pointing out of the paper, right? So basically, in this case, your induced magnetic field is parallel to your applied field, okay? So this is a general picture to what we covered last week. But starting from now, we feel the need to introduce a new vector quantity. It's called the magnetic field intensity. So starting from this moment and onwards, you need to understand what is the difference between this H, the field intensity, as compared to B, the flux density, right? Again, to recall your memory, in electrics, we first introduced E, and then we marched into D. E is the electric field intensity. Okay, so this is intensity. And D is the flux density. But think back, when we introduced magnetism, we first introduced B, which is called the magnetic flux density. And now we introduce H, the magnetic field intensity. Let me just add field. Okay? So today is very important, and probably the reason why I called you back into the classroom, because we need to clarify these 4 field quantities today, right? The entire semester, we are learning no more than these 4 field quantities, right? So today is the pivotal class. So you are right to come back. So let me tell you the story. We learned about Ampere's circuit law, and that tells you curl of B, we move this mu 0, the vacuum permeability, to the right. So curl of B is equal to mu 0 times J. But before today, we only said that J is the current density. We didn't specify what type of current density it was. But starting from today, because we're dealing with materials, we have to divide the current densities into two types. So J can be classified into J free and J total. So what's the difference? Well, if you don't understand the current densities between the free current and total current, that is okay because we haven't really discussed. But think back. What about rho? The charge densities can also be classified into two types, right? Rho free and rho total. You just finished your second examination, so you should still be capable of explaining which field quantity is associated to which, right? Free charge density is related to D, while the total charge density is related to E. So today, I'm going to explain, well, B or H, we now have two remaining vector fields. So in the same analogy as electrics, D is related to rho free, E is related to rho total. Somehow we need to assign either B or H or either H or B. Okay? So what I'm telling you is each field quantity is physically related to one type of source, right? Up front, I'm going to tell you B is related to the total current density. Okay? So let me use a colored chalk. The reason will become evident later, okay? But right now, let me just tell you, B, this field quantity, the magnetic flux density, is related to the total current you have in space, right? So can we decompose the total current density into its constituents? How can we formulate the total current density? Well, the total current density is actually your free current density, the current you apply externally, plus the ones you induced by having a magnetic material, right? As I mentioned, if we have a magnetic material, then we have the chance to generate induced magnetic dipoles. And we also learned if we have induced magnetic dipoles, we can have the chance to have a non-zero magnetization vector M. And having that M can give rise to a new current source, right? If you still remember, it's either curl of M or M what? Cross the surface normal, right? So this is the surface current density, and this is the volume current density generated by the induced magnetic dipoles, right? This is what we covered last Wednesday. I think the OCW footage is not on the web yet, so you have to follow the live streaming. Okay, so this is why I'm providing this background information. Okay. So the total current density can be decomposed into your free applied current density and plus your induced current density. There are two parts. Of course, now we're looking at the material response in a macroscopic sense, meaning we're not looking at the origin. We're looking at the material as a whole. We're standing far away from the material. So in this case, if we have a non-zero induced current, that should be coming from curl of M, the volume magnetization current density, right? Because we're now looking at a macroscopic sense, right? Now, in this mathematical equation, we have two curl operations. The first one is operating on B. The second one is operating on M. M is your magnetization vector. If you want to have a non-zero curl of M, then you need to have some non-uniform magnetic material, right? Otherwise, curl of M goes down to 0. But somehow, can we combine this curl operation with this curl operation? Of course, we can do that, right? So we can move this one to the left-hand side. So now on the right-hand side, we only have the applied current density. And over to the left, we have the magnetic flux density intermixing with the induced dipole moments, okay? The magnetization vector. It feels weird to have two curl operations written independently. So why don't we combine M and B having the curl into just one simple curl operation? So now the equation reads, curl of this B, the magnetic flux density, divided by the vacuum permeability and minus the induced magnetization vector. So this entire thing having the curl operation would be equal to the current, the free current density that you applied. Remember, this is your applied current. Therefore, it's free. So up to now, I only talked about the mathematical procedures. But then it feels weird to always write this complicated something minus something, right? So why don't we quantify? Why don't we define this thing within the bracket as a new field quantity? Let's just call it H. So starting from now, H is your magnetic field intensity. It is also a vector, and it is defined by B divided by the vacuum permeability and minus your induced magnetization vector. So up to now, this is purely mathematical and purely definitions, right? But then somehow, after summarizing all these findings, we now have a new equation. It's really not new. It's still called the Ampere's circuital law. But whenever you have materials, the material has certain magnetic response, then you have curl of H is equal to your applied free current density. Right? So this is written in the differential form. In the integral form, you have this. So if you perform a closed contour integration, H dot dl over this closed contour, you encompass the number of free current you have. Okay, so this is called the new Ampere's law in materials. So a direct comparison. When in vacuum, you have nothing. Ampere's circuit law is written as B dot dl having a closed loop integration is equal to mu, is I. Right? Remember, because you have nothing in vacuum, so you don't have any way to generate induced dipoles. If you want to induce dipoles, you have to have some kind of materials, right? So in here, this current is also the free current. Okay? But now if you have materials, materials could generate induced dipoles and therefore provide you additional amount of current source. So when you deal with the materials, you have to rewrite Ampere's circuit law using H dot dl is still I free. Okay? So they have the same name, but because, well, in vacuum, B and H is really pretty much identical. Okay? It's only having a scale constant. Scale is this, mu 0. Okay? So up to now, we redefined Ampere's circuit law. So starting from this moment and onwards, I strongly recommend you to accept and remember this form. Okay? Because ideally this form works for vacuum and heavy material. Right? Now, let's talk about the physical meanings. Okay? This is very similar to what I drew on the blackboard. If we have some magnetic material, if I only apply free current density through this material, as you all know, using the right-hand rule, if I apply some current flowing into your eyes, this current, well, assume this is a wire, a current conducting wire. It generates a circulating magnetic field line, right? Magnetic field lines are closed upon themselves. But due to this current and the generated field lines, you also have the possibility to create induced magnetic dipoles. Okay? And these are the M's. Okay? So the induced magnetic dipole field lines are always parallel to your externally applied field. Okay? And therefore creating some additional magnetization current. So together, you ask yourself, well, in this material, what is your total amount of current? And the answer is a simple addition of free current density to the induced current density. So together, you have the total current density of free plus the magnetization current. Right? So this is to explain from the current density point of view. If you're all okay with this picture, I'm going to move to the field line perspectives. Everybody okay up to now? It feels better to have students really in the classroom. There's no answer, but there are some nodding of the head. It feels good.